And the reason is because we have been having a math camp for the master's program and the PhD program that was ineffective for quite several years. The students are frustrated because they can't learn everything in 3 weeks. The instructor is frustrated because the students can't learn. And so we decided that we wanted to have an online version of it to try to help people to go over it. And so the strategy is very simple. So there is an entire course on YouTube, so you should watch it. And then the first hour of the lecture, of the class time will be office hour. So either, so after you watch the video, you will have questions, so you should ask me or the TA. Actually, you should ask the TA. And then the second hour will be a quiz. So we will explicitly ask questions from the material. It could be as simple as what is the definition of X, but it could be also calculations or proving something. Basically, the idea is to check if you understand the material. And then the last half, the third part of the class time will be, okay, so quiz time is over, please hand your quiz. Now let's solve the quiz question. And of course, what this means is that if you don't understand or you did very badly in the quiz, this is the time for you to learn. Okay? And this is supposedly an English speaking course. All of the TAs are actually paid according to the EMI TA rate, so they're obligated to speak in English. That could be a problem. So it's okay if you want to drop the course because of this. We did this because our math camp, I think, is also in English, so we wanted to be consistent. Okay. Any questions about this course format? Because next week is a holiday, so we will literally start from this week. Okay, so let me ask. So how many of you actually received the email from NTU from the TA? So some of you, okay. How many of you actually watched the video of the first week? Very good. Okay, so you all know that. Yeah. So the idea here is that we will. Yeah, because we wanted to find because next week is a holiday, so there is no other chance for you to actually experience this. So we decided that we will actually implement this format starting from day one. So that's now. So yeah, so if you watch the videos, then you supposedly you have a lot of questions to ask. And so please prepare to start to ask questions in the first hour. And then the next hour, we will start quizzing. And oh yeah, so in terms of the grading, so first there is a final exam that counts as 50%. So that's at the very end. So that's the final goal. So yeah, I mean, if you did very badly in the middle, that's fine. The key thing is the final exam. And then there will be weekly quizzes, like there is quiz one here. Actually, I put it on the back of the syllabus, so I can't give you the syllabus now because quiz one is on the back. But we will only count 10 quizzes of the weekly quiz. I think officially it's 16 weeks, but I think we have only, I forgot, 13 classes. So we will have 13 quizzes. And so the best 10 will count. And we also have an online option for you to take this online. Or I mean, if you are under quarantine or for whatever reason, then you will be able to take the quiz online. But in that case, that quiz, if it's counted, would only count for 1%, and your final exam will replace the remaining 4%. Okay, so yeah, so any questions about this format? Okay, so there were people asking about the problem about the YouTube video quality. Yes, because this is not our YouTube video, and it was filmed decades ago, quite a while ago. If you actually notice, I think it's 2014 or 17. It's more than 5 years old, so of course then the quality is not as ideal. And now we have iPhones that can take very good videos, but that's not the case in the past. And so, yeah, so actually the instructor in the YouTube actually has a blog, and in the blog it actually has a lecture notes section that has all of its lecture notes. I think I tried to link to the lecture directly to the lecture notes, but there were some problems. But you can still access it from the from the blog post. And so yeah, so if you're curious about what the instructor wrote on the blackboard, there is actually a screenshot version of that you can actually see the whole thing. Yeah. Okay, so any other questions before I hand this to you to start the first office hour? Oh yeah, one thing I'm curious about. So how many of you are econ students? Okay, so at which grade? At which year are you in? Okay, 大三、大四、硕一，有硕二以上的吗 ？Okay, very good. 然后what about everybody else？ 就不属于这个是哪些人？就不属于我刚刚举手，所以你们没有举手的是，所以呀，大五，哦 ，OK， That's fine， 对不对？因为 officially 大五 is still 大四，所以 yeah，but OK， 对，
大四
哦，辅系 OK，
我也是大四。
那你们本来是哪个系？
国系。
OK。Yeah, the only people I want to exclude are the people who are from the math department, because this is a simplified version of their second year requirement. 就是好吧，这故事我可以用中文讲，就是我在念数学系的时候遇到一件，你知道吗？数学系的书卷给奖规则有一条是他们只看主科成绩。原因是因为我记得我忘记是我大二还是可能是大三的时候，就是呢，我们系上有一个大四的学长，他去修了管理学院的管理数学，拿了100分，然后因为他大四学分都几乎没有修，他只修那一科就拿100分，就拿了书卷奖。然后所有的数学系老师都非常生气，可是按照规定还是要给他。对，那原因是因为管理数学其实是数学系大一的必修线性代数的简化版。那所以从此数学系就改了数学奖给奖规则，就是说他们只看主科，就只看他们数学只看 math 开头的科目，其他都不算。对，那同样的道理就是说，如果你是数学系的，你跑来上这门课的话，我会说，请不要来骗学分。Yeah, okay, so that's a story that I can speak in, I can tell in Chinese. But otherwise, yes. So anybody that does not belong to all these categories. 就刚刚还没有举手的是谁？所以你是大二 ，OK， 然后那你是
大四双主修，大四双主修，
所以你本来是哪个？
电机系。
电机系，我电机系 that's half， but OK that's fine。OK， 所以你大二来的时候是为什么？我不知道。好吧，应该这样讲，就是说，如果说你是大二或者好，我要先讲，其实我们当时设计这门课要开在下学期的原因，一来是说它是配合，就是说，比如说如果说你大四推甄上了，那你从11月推甄上到隔年的9月入学有10个月的时间，那可是你却没有任何的机会可以来上，比如说数学系的分析导论，因为他们的课是9月就开始的，然后是1整年的课，你不可能中间跑进去上，所以我们决定是2月开，就是下学期开，就是说，那至少开一个机会。那不过如果不是这样，如果说你本来就是9月就要规划你要上这门课的话，其实你应该直接去上数学系的那班就可以了，你没有必要来上这一个这样。 那当然是因为这样，所以我们学分数设计上也不太一样。好，那不过就是那个有了我上一个我认识大二就跑去数学去上数学课的人，他现在在念博士班，而且非常厉害，所以希望你可以维持这个传统。Okay, so yeah, so sorry. That was a survey of the audience that I think I needed to do. All right, yeah. There were concerns that there were too many people signed up for this class.
Seems like
Which is false. Yeah.
maybe like they see the first period is office hours, and they just don't want to show up for office hour. They may show up like in next period.
Oh, you mean people may show up right before the quiz starts?
Yeah.
Okay, but yeah, because apparently, yeah, because we have quizzes, so we were worried about this classroom being too small. Ideally, each one of you will be in one seat. Let's see. Actually, I think we do have enough seats for everybody. So everybody can use one table or one desk. Yeah, we actually have enough desks here. So yeah, actually. Anyway, so we'll see if more people show up, because we did request for a larger classroom if everybody that's on the roster shows up today, which apparently is not the case. But anyway, so okay, so now we can start. Oh, yeah, and if you don't know, this is the textbook. I have this version. This is my version. I bought it, I think in 1997, but I'm not sure. Yeah. So now you know how old it is.
And now the version is like the same.
Yeah, it's the same version, right?
Yeah, same.
Yeah. And this one is the other textbook. Actually, we have several reference textbooks. This one is very old. This one I bought in 1995. And to show you how crazy I am, so I read all of this, and I did all of the examples and homeworks. So I have like notes of all of your homeworks. This 1, 2, 3 pages, and so on, up to, let me see, up to 3.6, I think, and everything else is blank. Yeah. Yeah. So, but it took me like a whole summer to do 1.1 to 3.6, and for that reason, that's why I wrote explicitly in the outline of the course that I expect you to spend 20 hours per week outside of class. I'm not saying that you have to do that to get good grades in this class, but I mean, if you did not spend that and you're not getting good grades, you're not supposed to complain. All right, so those are the textbooks. I think I listed another online textbook, so that you can actually click and use online. There is another textbook written by Terry Tao from UCLA. I think that textbook, I forgot. I think that one is available through the university ebook system, but I'll have to double check. If not, then I'll have to try to order it. All right, so, oh yeah, the last thing is that, so in addition to the Francis Su videos on YouTube, there is also a Chinese video on NTU OpenCourseWare filmed by Chen Jinci, which is also based on the same textbook. But he has some crazy ordering, so you have to figure out which lecture corresponds to which. But for what I understand, Francis Su follows the textbook very closely, very diligently. So in that sense, if you think you can just watch the video and do not need to read the textbook, I think you're wrong. yeah, he follows the textbook almost section by section, chapter by chapter, and so I think it's essential for you to actually have the textbook and go through the textbook with him. All right, so I'll leave the remaining time to Zhongho.
So how about some self-introductions by TAs?
Hello. Okay. Hello, I'm one of your TAs. I'm Danny Boshenkan,
And I'm Sean Lan.
Right, I'm Zhenong. In this period, like we'll go through some questions on form. I think there's a question about like if you guys need to define addition, subtraction on integers. No, we don't need to do that. All right. So we suppose that everyone knows how to do the calculations on integers, and we also we only like need you to do those things on rational numbers. So yeah, in integers supposed. How about we go through it? Do you need time to read your notes, or I can go through and review some main materials? How about notes? So review by yourself. Raise your hand. Review by me. Okay, cool. So there are several main points. The first.
I should just start from the left, and I'll erase this for you. Just start.
Okay. So the first fundamental idea is sets. What do we like care about sets? Because like sets is the most fundamental unit in modern mathematics. So we're thinking about like if I say that there's a function f that is continuous. What I'm thinking about is okay, f comes from a set that contains all the continuous functions. Right? That just be the way like we think things. So when we see like when we see math, we're thinking about like there's a group of things interacting with each other. That's the way we see math. So maybe we should like group objects, right? Things like S equals to. I think in his example we use weird symbols, something like this. We'll do the same thing. Okay. So this means that okay, there's a set S which contains these three elements. So when we're thinking about groups of objects, we're thinking about their interaction. Of course, like care about some intersection or union. And those calculations are simple to you, I think. Like, for example, S1 equals to this one. And let's say S2 equals to cross and circle. Right. Of course, you have S1 intersect with S2. So we're thinking about like something satisfies the condition that S1 needs, and also satisfy the condition that S2 needs. All right. So like for example, we're saying that S1. We should go through this system first. So what was S1 intersect with S2? Anyone? X. How about S1? That should be final. Any question? No. Okay, so we're thinking about like this a weird example, but in real case, we're considering the example 1. In real life, or for real math, we're thinking about another example. For something like, okay, S1 is X, exponent. We usually denote it as R plus. And is that small? It's not. X is an integer. We usually denote this one as Z. Alright. So let's do this kind of thing again. What is Z? R plus Z. First things, can you understand this symbol? Yes?
Do we have to say that X is in R?
X is in R. What do you mean by X is in R? Oh, of course, like, yeah, but, you're right. But I think that's fair enough, like to discuss it, we need like more deep logical arguments, but we do not want to go through that kind of like too mathematical thing. Let's just be like logicians thing. So you can understand, once you can understand the symbols, that should be okay. Just don't like try to mess up with this in R or not in R. Alright, so what's this? This should be natural numbers. That's 1, 2, 3. Okay, cool. And what is, let's say, Z minus R plus? Just give me some elements in this set. Alright.
0.
0. As in -1, -2, etc. Cool. Okay, so after we're thinking about these sets, we're thinking about like once we have integer, once we have natural numbers, we're thinking about some relations on the elements of the set. So like which is bigger than the other one, or anything like that. So relation. The definition of relation, like if we say that R is a relation, on S. What do I mean by R is a relation on S? So thinking about this, relation is about like two elements in S. So we need some way to put two elements in S together. And that's the way we call Cartesian product. So there's a way that we product it together. Well, how we define this is A, B. A in S, B in S. If I'm too fast, just slow me down, alright? If you cannot like follow me, or if you have like any question to ask, just stop me. We're doing this, alright? So for example, when we think about n times n, we're thinking about like we're thinking about those thoughts. We're thinking about n by n cross n. We're thinking about this one. So this one may be more 1. from the net. Okay? Let's make some examples, like real life example. Example. How about we think that S equals to, we'll just write as the set of human beings. So we can like consider some relation. A relation should be ARB means A is the father of B. So in this case, R should equals to AB, where A is the father of B. Clear enough? But of course, we're not thinking about like this kind of relation in math. We're thinking about other relation. We're thinking about that if one is larger than the other. So we're thinking about order. So what is order? Order is kind of relation. So it's kind of relation. It satisfies like something that we write it in this way. So there are several. First one is that one's called transitivity. So I think I have read. Let me check it if I follow my. If I follow my things that you do this kind. I forgot if you do this relate this order or let me check. Do you use equal version or this version? Sorry, I forgot.
This version.
This version. This version. Okay. So they do another equal thing. Okay. Cool. It's first transitivity, and another one is one of the following groups. That A larger of B equals to B, or B larger than which means. I'm not so sure what it is in English, but in Chinese we call it 三一律. So we're thinking about this kind of order. Actually, we're not thinking about the real order, like the magnitude of the numbers. You can like define the order in a very strange way. Of course, the magnitude of order is the usual order you use, like for another example. One is the usual of R. I don't think that we need to go. Or maybe we go to this one, right? So now you see this, it's not just a symbol, it's a set. Okay? So this set concludes something like phi 3 or pi 0. You should see this one as a set. And of course you can define like another kind of order. Think about, we'll say that okay, maybe on we'll do this. We say x, y, f, x, and 4. Can you see? If no, I can write it like upward here. That's kind of order. So the order would be like, use another color. This one is R, this one is 0. So this one is the largest. And if you go this way or this way, the thing will go smaller. I mean, in this order sense. Alright, so we'll write it something like 0, 1, negative 1, 1.5, negative 2, something like this. You can check yourself, check by yourself that this one is old. So, by econ sense, we're all econ students, right? So in econ sense, we're thinking this kind of order as something like preference, but with no indifference objects. So we're saying that, okay, I think there's no rule that what things you're more preferable or anything like that. There's like free rule for you to choose. So we're not saying that, okay, when you have like more objects, you'll like more like the option. Maybe like it's too much for you to consume. Good. Order.
Yeah, so I have a question. So why is a small, lesser, the absolute value of x is lesser than 1, or the absolute value of 1, not greater?
It can be greater, but
No, I mean, if you want to talk about preferences, I thought that the consumption bundle of x should be bigger than 1.
yeah, but okay, the two parts are different. One part I'm talking about, okay, you can construct this kind of order, and another part is you can put this kind of order into a sense that we're talking about preference.
Okay, so this is a very weird order relationship that.
Yeah, this one is weird.
Yeah, so greater is actually smaller.
Yeah, and smaller is so smaller. Like here's one is like some sweet point. You do not want to change, but if you change, like the positive change is better.
Yeah, I mean, this is weird.
Yeah, this one's weird. I agree with that. I just come up with.
I mean, yeah, I mean, you're messing up all of our our intuition, right?
Sorry.
No, but, okay, I mean, it's good in the sense that, I mean, because mathematically, this is perfectly correct. Of course, this is against all of our,
Yeah, this one is not in your intuition.
it's purposely to be the opposite of what you think.
Yeah.
But, yeah, but I just wanted to clarify that everybody understands that this is a very weird example where actually greater or x greater than y actually means x is smaller than y.
Yep. Any problem? Questions? No? Cool. I've gone through sets, relation, order. Do everyone knows like how to do the proof of s squared equals to I mean like this one. Everyone knows how to do this proof? If you want to like me go through this proof, raise your hand. If no, I'll skip this part. Okay, this one. So the spirit of this proof is like we want to calculate it out. So if there is a rational number, then what is it? Right. So proof. That x squared equals to right. So because we want to calculate it out, right? We'll give it numbers, P and Q, and we'll say for simplicity, the greatest common divisor of P and Q is 1. So, P squared, Q squared, over Q squared equals to 2. Because this one is x squared. Which means that P squared equals to Q squared times 2. What do I mean by this? What can I imply? That P is a multiple of 2.
Wait, so before you go on, so PQ are in Z.
Yeah, PQR,
are in Z.
yeah. PQR in Z.
And so when you say for instance PQ equals to 1, that means that there's no common.
Yeah, there's no common divisor. Yeah. PQ in Z. PQ equals to 1. So we can write, take P equals to 2P prime. P prime is also in Z. So we have P squared equals to 2Q squared, which means that 2P prime squared equals to 2Q squared, which means that P prime 2P prime squared equals to Q squared. This gives us that Q is a multiple of 2, which leads to a contradiction. because P is a multiple of 2, and Q is also a multiple of 2. But we say there is no common divisor. That's one way to do this proof. And another way, let me proof 1. Another way to do this proof is through your high school algebra. Like by, I forgot the English. Can I write in Chinese? 牛顿一次因是什么吧？
You should have a Google Translate of you. Oh no, ChatGPT.
Yeah. So the only possible roots, rational roots, for x squared minus 2 equals 0 are 1, negative 1, 2, negative 2. But none of these is the root of it. So dumb. Too fast or not? I hope not.
I do have a question. So, the method you appeal to, is that already based on the rational number system?
No,
No, it's not. Okay.
it's not. It's not. I've checked it.
Okay.
Okay, I think the last part is about the field and order field. I will not take you go through all this axiom. Right, because the axiom is too complicated. And I want you to appreciate this kind of axiom system. Like this kind of abstraction is not a way to lead us to nonsense, but a way to help us to identify what is important or what are we actually dealing about. So in let's say micro theory, you'll learn about some rigorous definition of preference, or some rigorous definition of let's say the positive would be macro theory. But what I'm trying to say is in income theory, we'll deal with every single rigorous definition, and you need to think it in this kind of way, so that you know whether handling with. Cool. Cool. Maybe I just go through some preposition. Maybe it skipped on the material. It would be from rooting. So it's a red book the teacher just showed you. Rooting. I think everyone should go through this preposition after this class. Alright, do it yourself. I'll just pick several things and to show you how to do this kind of metric. First one is example 1. Any idea? So we want to say that x equals to this one. The negative of negative x. So what do you mean by negative of negative x? Let's start from the definition. What's this one? This one is the object that's combined with negative x and we go to 0. Alright, so the thing, we all know this about this one is that negative x plus negative of negative x equals to 0. This one, this is the definition of this negative. So from this, maybe you can guess that maybe we need the property x plus negative x equals to 0. And somehow cancel this, then we can have x equals to negative of negative x. Okay, that's the idea. So let's go to a proof. Proof. So, x plus negative x equals to 0 equals to negative x plus negative of negative x. How about we put this from the first? We have this one plus negative x. It convenes, right? Yeah, it deconvenes, so we can do this. Then x plus negative x plus negative of negative x equals to negative of negative x plus negative x plus negative of negative x. Why I'm trying to do this is because what I have just said, I want to cancel out this term. So I just not just pop up with, okay, let us plug in this kind of weird thing here. As the intuition behind that is because the definition of negative is this equation, so that we come up with this property. And we want to link this one and this one. So we want to cancel this term. This term here is the way how we cancel all these terms. Right? So by associativity, we can do this. By definition of additive inverse, gives you x plus 0. And this one will gives you negative of negative x plus 0. And we know by additive identity, we know this one is x, and this one is negative of negative x. So prove this one. Right. You need to do this kind of thing on quiz. That's just like one simple, or one question only. Right. Let me check.
sure if I follow the proof of this one.
This one?
Yeah.
So the first step is that we know x plus negative x equals to 0.
Yes.
And we also know negative x plus negative of negative x equals to 0.
Yes.
And we like, because the activate commute, so we put the negative x to the behind of the negative of negative x. We do the reverse. This is the first equation.
So you mean that because a plus b equals to
B plus A, yeah.
Okay, I see.
And so because we put negative x on the behind, so we can plus of negative x to the two equations. We can cancel out.
Wait,
this one.
so both of these are 0, so you add 1 to the end.
Yeah, I add negative of negative x to the end.
I see, okay.
And its purpose is to cancel out negative x. Yeah.
Yeah, but, yeah, that has to be, all of this has to be explicit otherwise.
Another trick. Example 2. Let's do this one. Negative x equals to negative 1 times x. Any idea? So, like, again, we return back to our definition. What's the definition of negative x? It's the term that x plus negative x equals to 0, right? So what we want to show is x plus negative 1 times x equals to 0. That's the intuition. That's what we want to show. All right. From this, how do we come from this? So you may think that okay, there's 1. So what is 1? What do we mean? What do we mean by 1? That's 1 times x equals to x. That's 1. Right? So this 1 is actually equals to 1 times x. Okay, from this we can do our stuff. Right? X plus negative 1 x equals to 1 times x plus negative 1 times x. It equals to 1 plus negative 1 times x. It equals to 0x but is 0x 0? Well, first assume it equals to 0, and we turn back to deal with this problem, alright? So we do a thing here that's, okay, maybe equals to 0. But first suppose it equals to 0. So we have what we have. All we have is x plus this one equals to x plus negative x. Can you see? If no, I have my range here. It's okay for you? Okay, cool. X plus negative 1x equals to x plus negative x. So from this, we can do the same trick we have done here. That is, we put x backwards and cancel x. So you have cancellation law and obtain this one. But why 0x equals to 0? This one is like a little bit harder. Any idea?
Using the distribution.
Use the distribution law. Yeah. How to do with the distribution law?
1 plus 0 times x.
1 plus
0 means that if you x at 0 equals x.
How about you I give you chalk.
Okay.
You can show it.
This is the definition of 0.
Yep.
And so, know that 1 plus 0 x also equals 1x and equals x.
Yep.
So x plus 0
X.
equals x plus
X plus 0 equals, yeah, yes, you're
so
right. So x equals 0 equals to x plus 0x.
and you
And you cancel out x,
Yeah.
I've got obtain 0x equals to 0. Alright, can everyone follow this proof? So what you do is to use the distribution law and to construct a term called 0x, but on the other side there's nothing constructed. Because there's nothing constructed and there's 0x, so 0x must equals to 0. Cool? Okay, so I think that's all of this period, and hope you did a good job, do a good job in your quiz in next period. Cool. Any question?